Hi everyone, my name is Jessica Iwamoto and I'm from the Aerospace Corporation. And today my talk is going to be on accelerating software radios by means of SIMD instructions, a case for the AVX2 and AVX512 intrinsics. Specifically, we're focusing on acceleration through VOLK. And you guys have probably all heard of VOLK. It's the vector optimized library of kernels. You've probably had to install it when you've installed GNU Radio and run VOLK profile to set it up. But for those of you who aren't super familiar with exactly how it works, VOLK is basically a library of operations that are optimized for a specific processor. And it's used widely in GNU Radio, as well as the other open source softwares like GNSS SDR. And it's used in a lot of signal processing to perform fast mathematical operations. What's neat about VOLK is it'll run on basically any architecture, and what it does is it determines which set of instructions or which implementation of a kernel will run fastest on your architecture. So it's really nice because any user can just take VOLK, install it on their computer, and set it up. And then when they run GNU Radio, they'll be ensured that GNU Radio is running with the most optimized instructions for their architecture. And this is super powerful because it makes GNU Radio portable, and so it can be run on basically any type of computer. So stepping back first, everyone knows that computers have been getting faster and faster over time. Every year they seem to be performing better. But what explains this trend? Well, if we look in this graph of processor metrics over the past 50 or so years, we can see that the frequency and power of processors has been getting faster and faster over time up until like the mid-2000s. And this probably explains the increase in performance of computers, at least during that time period. However, after the mid-2000s, it looks like power and frequency both level off. So what then explains the increase in performance? The answer is parallelization. So as you can see, the number of logical cores has been steadily increasing since the mid-2000s, and this means that computers can operate on multiple CPUs at once in parallel, and thus increase their throughput. So there are several different types of data parallelization techniques. The first is instruction-level parallelism. This occurs when compilers try to organize instructions such that all functional units and paths to memory are busy at all times. However, studies have shown that for typical applications, it's only possible to organize 3 or 4 instructions to run in parallel in this way, thus limiting the reach of this approach. Second, we have task parallelism. This occurs in shared memory parallel computers when computers operate multiple instruction streams at once on different processors. And then finally, we have data parallelism. And this occurs when we operate on multiple data elements in parallel. This is also known as SIMD, or single instruction multiple data. And this is the type of parallelism that we'll be focusing on this work. So a bit more on the Intel SIMD instructions. Intel has released several libraries of SIMD extensions, starting with MMX about 20 years ago in 1997. MMX was originally released to support graphics and multimedia operations. And some examples of things that were used in were games like POD and Half-Life. It was also used in an MPEG-2 video encoder, and MPEG-2 is the standard for digital television video. And it was also used in MP3 video, MP3 encoders and decoders. Next, 2 years later in 1999, Intel came out with SSE, which introduced a 128-bit wide register. And this also had a much wider set of instructions for floating point and arithmetic operations. After that came AVX in 2011, and then a little bit later, AVX2. And these introduced a 256-bit wide register. These were used in a lot of signal processing and image processing applications. So MATLAB, Excel, Adobe Premiere, Adobe Photoshop. And these are probably the instruction sets that you'll find on your computers today. So if you went out and bought a machine today, it would probably have up to AVX2. And then finally, there's AVX512, and this has support for up to 512-bit registers. This is only available on select processors, such as the Xeon Phi processors. So there are less applications that use it, but some that do use it are X264, which is an MPEG-4 video encoder, and RPCS3, which is a PlayStation 3 emulator. So when we started this project, VOLK was lacking support for AVX2 and FMA, which is a subset of AVX2, and AVX512. And so what we worked on is adding support for these instructions to VOLK. And this right here is just a diagram of the register sizes. With SSE, there are only 8 registers. With AVX, there is an increase to 16 registers, and then with AVX512, we got 32 registers. So for AVX512, there are many different subsets of AVX512, and as I mentioned before, they're only operated on certain processors. So this plot right here shows the different subsets of AVX512 and which processors support them. So as you can see, AVX512F and CD are common across all processors, and so these are the versions of AVX512 that we chose to target with our work. AVX512F is the foundation set, so it basically contains all of the data manipulation and mathematical operations in AVX2 and AVX, except for 512-bit registers. Next, we have AVX512CD, which is the conflict detection set. So these deal with detecting memory conflicts. And then there's AVX512ER, which contains instructions for exponential and reciprocal. There's also AVX512PF, which contain prefetch instructions, AVX512BW, which contain byte and word operations, so those are 8-bit and 16-bit data types. We have AVX512DQ, which are the double and quad word operations that operate on 16-bit and 32-bit data types. And then finally, there are the AVX512VL, which are the vector length operations, and those operate on the 128-bit registers and the 256-bit registers. So in our development of VOLK, we use the Intel C-style intrinsics. These are basically C functions that provide direct access to the Intel intrinsics that were previously only accessible with assembly code. It's important to note that SIMD isn't supported by all architectures. However, VOLK supports a much wider variety of architectures than just these. VOLK actually was designed as fixed to portability problems. So what's great about VOLK is the user doesn't have to make any changes to code when they switch architecture. VOLK just figures that all out. So at its base, VOLK is a set of protokernels that are designed to operate on different SIMD architectures, runtimes, or particular platforms. And what happens when you compile VOLK is only the protokernels that are supported by your architecture are compiled. And then when a kernel is called, VOLK resolves the kernel call to a specific protokernel. In order to choose which protokernel, VOLK runs a test through all of the possible protokernels and determines which one's fastest. So in this way, you're always ensured that the fastest protokernel for your architecture is being run. And this is, again, it's really important for GNU Radio because it makes it portable and it makes it really easy to run. So in the next few slides, I'm going to go over basically a programming model for the VOLK intrinsics. It's pretty simple. So on the left here, we have basically the pseudocode for one VOLK protokernel. At the top, we have the macro that is basically a safeguard to make sure that only supported architectures are compiling this protokernel. Next, we have the function description. They all start with VOLK, and then they have an input tag, which is basically the input data type and data size. Next, there's the kernel description, which describes what the kernel does. So it could be multiply, add, or something more complicated like square root, tangent. Next, there's the output tag, which again is the output data type and data size. Next, we have the alignment. So this indicates if it operates on aligned or unaligned memory addresses. And then finally, there's the protokernel description. And this describes basically what architecture it runs on. So that could be AVX, AVX2, et cetera. Going down, we have variable descriptions, and then we start our loop unrolling process. So what happens in this loop is we operate on chunks of the register size. We load them from memory, perform the operation on them using the SIMD intrinsics, and then store them back into memory. We continue this loop until we've gone through all the multiples of the register size, and then for any data that's not a multiple of the register size, down here, we just perform the operation in serial. So that's non-optimized. This right here is an example code for a protokernel. This is the multiply protokernel for AVX512F. And so again, at the top, we have a header that makes sure that this is only compiled on architectures that support AVX512F. Then we have the function name. So we can see it's 32F, which means it's a 32-bit float input. The X2 indicates that there are 2 inputs. Next, it's a multiply function. And then 32F, again, indicates that the output data is 32-bit float. The U indicates that this operates on unaligned memory addresses. And then AVX512F indicates that this is for AVX512F. Going down, again, we have variable declarations. And then we begin our loop unrolling. So first, what happens is we pull out chunks of 512 bits from memory. Then we perform the multiply, and then we store the chunks back into memory. Again, we repeat this until we run out of 512-bit chunks. And then with the remaining data, we just perform the operation in serial. So the whole point of this, basically, is that it's really easy to develop these VOLK protokernels. It all follows a model. And is pretty simple to develop. So it's pretty simple to, as Intel comes out with new intrinsics, or if there are similar extensions for other architectures, it's very easy for us as a community to keep VOLK updated and continue to leverage the advances in technology. So as I mentioned before, we added AVX2 and AVX512 to VOLK. And in order to check our results and check the performance, we use VOLK's internal profile, VOLK profile. And what it does is it runs a randomized set of tests on your protokernels, and it checks that their result is correct, and then it also times the results so we can see how they perform in relation to other protokernels. We ran all of this on a Xeon Phi Knight's Landing processor. What this is, it's a many-core processor developed by Intel. It's designed for high-performance computing applications, and it's 64 cores, 4 threads per core. And our department basically bought this computer just as an experiment to see if we could increase our throughput for our real-time software-defined radio applications. The following results are going to compare the master branch of VOLK as it is now to our changes, which I will denote as the next branch. We currently have a pull request open in VOLK right now, and we're just waiting for the CLA to go through. So hopefully you guys will see our improvements pretty soon. Another thing to note is that in the following results, we're only interested in the relative time differences between the 2 branches, not the absolute time differences, as this only is a product of the processor clocking rate. So here are just a selection of our results. As you can see, we have various protokernels and then the fastest architecture for each protokernel. You'll notice that there's 4 points per protokernel. That's because the top 2 are for the best unaligned architecture, and the bottom 2 are for the best aligned protokernel. The black data points indicate the master branch, so that's the version of VOLK that's currently there. And then the gray ones indicate our improvements. So we'd hope that our improvements are much faster than the master branch. In total, we improved 82 kernels by adding AVX, AVX2, FMA, and AVX512. We added AVX2 and FMA to pretty much all the kernels that we could, and then we added AVX512 to a subset of them. Previously, we noticed that in the master branch of VOLK, most of the kernels had their best architecture as just generic or SSE. Generic is especially slow because it is the just serialized, non-optimized version. And so here is a selection of our results when we added AVX, AVX2, and FMA. You'll notice that for a lot of these protokernels, the improvement is 50% or more, which is really great. And the fastest one is right here. That was an improvement of 94% for the square root kernel. We also noticed that greater performance gains were achieved when we added AVX2 to the kernels that required more mathematical processing, so like square roots and tangents, as opposed to the simpler ones like multiplies and adds. And that's just because the more mathematically intensive ones required more instructions, and thus there were more instructions for us to optimize. It's also not shown here because here we're only showing the fastest kernel, but we noticed that when speeding up from SSE to, say, AVX, the improvement was much greater as opposed to when changing from AVX2, or AVX to AVX2 and then AVX2 to FMA, as those gains were only about 10%. Next, this is a summary of our AVX512F results. So as I mentioned before, we only added AVX512 to a subset of the kernels, and that's because the lack of permute, XOR, and shuffle operations limited what we could improve. So we were only able to improve simpler kernels. And that's why you can see in the graph, there are some improvements, but they're not as big as in the slide before. It's because we could only improve the simpler kernels. However, we expect that if we were able to use the other subsets of AVX512 and add AVX512 to the more computationally intensive kernels, that we would be able to see much greater performance gains like we did in adding AVX and AVX2. So in conclusion, our additions of AVX2 and AVX512 will greatly increase the performance of GNU Radio and any other real-time software applications that use VOLK, such as GNSS SDR. Our improvements were only tested on a Xeon Phi x86 processor. However, we suspect that due to compatibilities with other processors, our improvement should also work on similar processors. We also postulate that because AVX512 is only capable in x86 processors, that we could do something similar with extensions for other architectures like ARM. And further work on this project will focus on adding AVX512 of the other subsets, so like AVX512BW or DQ, and being able to add AVX512 to all of the VOLK protokernels and hopefully see great improvements there. And finally, the bottom line of this is that we've seen that our additions of AVX2 and AVX512 have greatly increased the performance of VOLK. So it'd be pretty neat if we as a community could keep VOLK updated with the latest Intel instructions and similar extensions for other architecture, as this will greatly improve the performance of VOLK and benefit the entire community of GNU Radio. We'd like to acknowledge the following people for their support and funding on this project. And of course, my co-author, Damien, who couldn't be here today, also had a big part of this project. Finally, these are our references, and thank you for listening.
Okay, we have plenty of time for questions, and after questions, there will be some short announcements before we go into a break. Okay, I'm going to start over here with Ian, and someone can handle that side.
Great presentation, very interesting. So you've obviously spent a lot of time looking at the various flavors of SIMD available for x86. I'm wondering if anything has leapt out. You say, as improbable as it sounds, let's say we're designing a new microprocessor for SDR. Are there any specific categories of function or anything that just are not well represented in the SIMD instruction sets that are available in the various x86s?
I mean, I didn't notice anything sticking out that...
Is there good, for example, saturated arithmetic support?
I guess I mean, we weren't really going through and like adding any new functionalities. We were only improving on the proto-kernels that were already there. So for the kernels that were already there, they were using certain instructions, and so we kind of just were upgrading those and making
Sure, you were enhancing what was already in VOLK, so perhaps the original authors didn't ever. Yeah, okay, that makes sense.
Mostly that, yeah.
I think we had one over there.
So, hey, thanks, great talk. First of all, just to comment on Ian's question, yes, there is awesome saturated logic that's basically just a flag in the FPU registers to saturate or not. Other than that, I remember AVX having, like, on early versions of the chips that supported it, they had the issue that a lot of that was like implemented in microcode, and things actually slowed down when you started using that because they had to scale down the CPU frequencies. Did you see that happening? Like reduced CPU frequencies as soon as you started using AVX 2 and 512?
I don't know. I wasn't really.
I mean, overall, the performance speaks for itself, right? I mean, obviously, it's great. Okay.
I guess, yeah, I didn't really look at how the CPU frequency changed.
Okay, cool. Thanks.
It's like lots of questions. So, Brent, can you go over there? I'll go back here.
Hey, I was just kind of wondering what compilers you guys were using when you did these tests. Obviously, newer compilers that are aware of the ability to vectorize to the collision detection type registers might be able to produce code from the generic results that is using underlying AVX instructions. So I was just kind of curious what versions of what compilers you guys use. Did you guys use ICC or the latest GCC, and what kind of OS?
We were just using GCC.
Thank you.
We were just using GCC.
Is it a recent version of GCC? Was it? Just kind of curious because the older versions of GCC probably won't have the knowledge of the new instruction sets.
Yeah, like a fairly recent version. Yeah.
Okay, cool.
Hi, did you, so at the end of every VOLK kernel at the bottom, there's that generic part that has to go through and do the remaining elements. Did you try using like any of the AVX2 masked load instructions to get over that hump? Because I've done a lot of work similar to this, and having that part of the loop in there, I find that if you do like kind of like work stuffing where you just round up to a register size, you get a lot higher performance than if you have that little loop at the end. So I was just wondering if you guys did any research on that.
No, we didn't do anything like that. I think we figured that the bulk of the time, like basically that little part at the end wouldn't take up that much time in relative to the rest of it. But yeah.
I think there were more questions.
Hi, good presentation. One question I had was, did you guys look at how well those results on the synthetic benchmarking translated to real world, like new radio application performance?
Right, so this project basically stemmed from projects we were doing in GNSS SDR. So we were trying to improve VOLK in order to improve GNSS SDR. So we did find that we did see performance improvements, I guess, for the specific thing we're looking at in GNSS SDR. I haven't tried anything in GNU Radio because that wasn't our focus of the project, but I would hope and suspect that there probably would be one, given the performance improvements of the individual kernels.
Thank you. Very interesting talk. All the AVX 512 instructions are not on the standard CPUs, right? My desktop won't have some of them.
Probably not.
Have they left out like any useful instructions? What's your opinion on that?
From AVX 512?
Yeah.
I mean, I guess, as I said, we only really added AVX 512 to the more of the simpler kernels. So we're really looking at what is available, like everything that's available on AVX 512. But yeah, AVX 512 is only available on certain processors for Intel.
All right, actually I have a question. So first of all, I'd like to thank you for going the extra mile and like doing the CLA and trying to upstream all of this. That's fantastic. We don't get that often enough, and I think it'll accelerate lots of people's SDR applications. So thanks for that. Now, one thing here's my question. The thing I didn't even know about until I saw your talk was there were these prefetch and scatter-gather operations.
Mm-hmm.
I mean, for VOLK, they kind of don't know if they really make sense because we do like data in, math, data out. But did you look at those? And I mean, could we start using those for, I don't know, maybe connecting GNU Radio to some DMA, based SDR to get data more quickly into GNU Radio?
Yeah, I didn't really look at those much because we wanted to use the AVX instructions that were like most compatible with all the processors there. So we really mostly just looked at AVX 512F. But yeah, they could be useful. Yeah.
So which CPUs have the PF construction set?
I don't. So the Knight's Landing one, yeah, we were testing on a Knight's Landing processor.
Okay, final chance to ask a question. Oh, this one here.
Also, thanks for actually doing a contribution in PR. It's great, and sorry for taking so long to ask about the CLA. Do you have results? I know that you did a FMA version of the rotator. Is there a reason, did the AVX 512 not support, did it not have instructions that were good for the rotator, or is it just a matter of time and effort?
I think, yeah, for that one, yeah, for a lot of the AVX 512 stuff, it was either AVX 512F didn't have the right permute or shuffle bit moving instructions, or we also just kind of ran out of time and funding.
Yeah. Also, I didn't see it on the chart. Do you have performance numbers for how the AVX or the FMA helped the rotator?
We probably do. I don't know if I included it on these results.
It has a weird input string.
Yeah,
so it's like the
so
VOLK 32 FCX2.
I don't think so. Since there were like 80 kernels, and I only included like 30 of them in these charts. But if you're interested, yeah, feel free to talk to me after,
All right,
and
yeah, great.
I can look
Thanks.
at that.
Okay, one more big round of applause, please.